Today we're going to talk about a very important concept in complex analysis, that of analytic functions. A complex valued function f of z is analytic on some open set u if the derivative of f with respect to z exists for each z belonging to that open set u. So what we mean by an analytic function, we mean a function that's differentiable at every point in some open set. And some books mention a condition of continuity of the derivative to call a function analytic, but there's something called Gorsaw's theorem that states that whenever the derivative exists, it will be continuous, and we'll cover that in the later part of the course when we're studying integration in the complex plane. There's also a notion of being analytic at some point, as in at some complex number z naught. So we say that f of z is analytic at some z equal to z naught when it's analytic on some open disk centered at z naught. Now, what is it exactly that makes a function analytic on some open set? Or can I rephrase that question to ask if there is some way to determine whether a function is going to be analytic on an open set under consideration or not? Well, thankfully, there is an answer to that. There is a way that we can determine a function to be analytic or not, and for that, we need to write f of z first in terms of its real and imaginary parts. And we know that the real part u is a function of the real and imaginary parts of the complex variable z, and the same goes for the imaginary part v. So what behavior of the real and imaginary parts of the function under consideration guarantees it to be analytic? There are in fact two conditions that form the necessary and sufficient conditions for a function to be analytic. The first one of these is the Cauchy-Riemann equations, or the CR equations, which by their very name makes it a big deal because, well, Cauchy and Riemann. So what are these equations? Well, these equations are partial derivative of u with respect to x equal to partial derivative of v with respect to y, and the partial derivative of u with respect to y equals negative partial derivative of v with respect to x. So those two are the CR equations, but the mere satisfaction of these equations on the given open set under consideration does not guarantee the function is going to be analytic. There are functions that satisfy the Cauchy-Riemann equations, but they're not analytic. So what seals the deal here? That is the condition of the continuity of the first partials of u and v on the open set u under consideration. Of course, you're not supposed to believe everything your teachers tell you, so you should ask for a proof. A proof that these two conditions together form the necessary and sufficient conditions for a function to be analytic. So let's check that. First up, let's see what happens when we say that f of z is analytic. So if it's analytic, that means it's differentiable for any z naught belonging to u, correct? So that means the derivative at z naught, defined as the limit of f of z minus f of z naught divided by z minus z naught as z approaches z naught, exists. So let me just expand f in terms of its real and imaginary parts. And z approaching z naught is equivalent to xy approaching x naught, y naught, where x naught, y naught are the real and imaginary parts, respectively, of the complex number z naught. So that means the derivative at z naught equals the limit as xy approaches x naught, y naught of u of x and y plus I times v of x and y minus u of x naught, y naught minus, I need some writing space, so let me just make some adjustments here. Okay, cool. Minus I times v of x naught y naught divided by x naught plus I times y naught. No, wait, it's the z first. Terribly sorry about that. X plus I times y minus x naught plus I times y naught. And now let me just collect the u's and b's together. So I'm writing this as the limit as xy approaches x naught y naught of u of xy minus u naught of x naught. I could call this u naught, but nah, it's much better calling it x naught y naught. Plus I times, now for the imaginary parts, v of xy minus v of x naught y naught divided by x minus x naught plus I times y minus y naught. The fact that this limit exists means only one thing, that regarding the point x naught y naught, it doesn't matter along what route you approach this point. The limit is path independent. No matter what route you pick, you're always going to end up with the same value for the limit. So let's evaluate the limit along two distinct paths here. One is a horizontal line in the complex plane. So horizontal line means that the imaginary part of z is always going to be equal to the imaginary part of z naught. And another path along which we're going to evaluate the limit later is a vertical line. That is now the real parts of z and z naught are equal. So let's evaluate the limit first along this horizontal path. Along the horizontal path, we see that we're evaluating the limit as x approaches x naught of u of x y naught minus u of x naught y naught. And let me just move this somewhere else. I think we're going to be okay here. Yeah, much better. And yeah, those were the u's. Plus I times v of x y naught minus v of x naught y naught. And this is all supposed to be divided by y minus y naught is now 0. So we're left with x minus x naught. Okay, cool. This limit that we have in orange is the derivative of f at z naught. And because we assumed f to be analytic, that means it's nice and differentiable. That means the real and imaginary parts need to be differentiable as well. So that means I can invoke the linearity of the limit operator because the two limits formed exist. That is the limit as x approaches x naught of u of x y naught minus u of x naught y naught divided by x minus x naught plus I times the limit as x approaches x naught of v of x y naught, oh, terribly sorry about that, minus v of x naught y naught divided by x minus x naught. And we know what exactly these limits are, right? The first one of these is the partial derivative of u with respect to x evaluated at x equal to x naught, or xy equals x naught y naught, that is, plus I times the partial derivative of v with respect to x evaluated at xy equal to x naught y naught. Again, terribly sorry about that. Much better. So this is the derivative of the function at z naught or x naught y naught, if you'd like to call it. So that's one evaluation of the limit along one path. And now for the other path, we're now trying to evaluate the limit along this vertical path. That is, the real parts of z and z naught are equal as we traverse this path. Okay, so what does that mean for us? Well, that means we're evaluating the limit as y approaches y naught of u of x naught y minus u of x naught y naught plus I times v of x naught y. Oh, wait, this is supposed to be x naught y minus v of x naught y naught, again invoking that linearity and all that, which you probably see coming, we have in the denominator, because x and x naught are equal, I times y minus y naught. So after splitting up the limit and all that, what do we get? We get 1 by I times the partial derivative of u with respect to y plus I divided by I times the partial derivative of v with respect to y. So the i's cancel out nicely, and we know what the reciprocal of I is. The reciprocal of I is negative I. So that means we have partial v by partial y minus I times partial u by partial y. So this is also the derivative of f at z naught. But hold on a second. Oh, wait. These are, of course, evaluated at, I'm just going to call it z naught here because of shortage of space for the x naught and y naught terms. Okay, so let's make a quick recap of everything we've done so far. We started off by saying that f of z is analytic, and that led us along two different paths. On one hand, we said that the derivative at any point z naught belonging to the set u, and of course we said that f of z is analytic on the set u. So the derivative equals the partial of u with respect to x plus I times the partial of v with respect to x. But along the other path, we said that the derivative, we found that the derivative equals partial v with partial derivative of v with respect to y minus I times the partial of v with respect to x. And because f of z is analytic, that means the derivative exists and is continuous. So by continuity, we see that all the first partials of u and v need to be continuous as well. And of course, the derivative exists, so it's unique at every point, meaning that these real and imaginary parts should be equal to each other. So equating the real parts, we have partial u by partial x being equal to partial v by partial y. And we have partial v by partial x on analyzing the imaginary parts equal to negative partial u by partial y. So starting off with f of z being analytic, we found that the partial derivatives, the first partial derivatives of the real and imaginary parts need to be continuous, and they need to satisfy the Cauchy-Riemann equations. But now we need to go the other way around. To prove that the conditions outlined earlier form a sufficient basis for f of z to be analytic, we start off with the assumption that f of z satisfies the CR equations with continuous first partials of u and v on the open set u. And we pick any z naught belonging to u and evaluate the limit as z approaches z naught of the difference quotient, that is f of z minus f of z naught divided by z minus z naught, and hope and pray that it leads to the conclusion of the function f being analytic. So let's expand f in terms of its real and imaginary parts. So I can write this as the limit as xy approaches x naught y naught of del u plus I times del v divided by del x, that is, plus I times del y. Okay, now we assumed that u and v have continuous first order partial derivatives. So that means del u approaches partial u by partial x del x plus partial u by partial y del y, and a similar relation for del v. So this implies that this limit that I'm just going to call L from now, the limit of the difference quotient equals the limit as xy approaches x naught y naught of partial u by partial x del x plus partial u by partial y del y plus I times partial v by partial x del x plus partial v by partial y del y, all of this being divided by del x plus I times del y. Okay, great. Now what? Now I'd like to collect the del x and del y terms together. So we're evaluating this limit. You know what we're approaching, so it's fine. I'm just writing this as limit partial u by partial x plus I times partial v by partial x, terribly sorry about that, times del x plus partial u by partial y plus I times partial v by partial y, all times del y, divided by del x plus I times del y. Okay, great, but now what? Well, I plan to factor out this entire term. Well, that sounds quite ambitious, but okay, why not? So we're evaluating the limit as xy approaches x0, y0, there at least I'm saying it, partial u by partial x plus I times partial v by partial x, del x all factored out, meaning we're left with 1 plus partial u plus I times partial v by partial y divided by this thing here that we factored out, partial u by partial x plus I times partial v by partial x, and we have this del y term, and we also factored out a del x term, right? So that means we can write this as del x by del y. We have these huge braces, and we're dividing all of this, remember, by del x plus I times del y, and I'd like to factor out a del x term from here as well. Okay, sure, why not? And the del x terms cancel out quite nicely. Now, what was the purpose of deriving such a structure? Well, notice something here. We have a term that is del y by del x, and this thing here is path dependent. For the point z0 or x0, y0, this term here varies as the path along which we approach z0 varies, correct? We pick a different curve, and we get a different del y by del x. Okay, so that's something that's path dependent, which is something that we don't want. We want the limit, and remember, this entire thing is still the limit of the difference quotient that I'm calling L. We want this thing to be path independent. We want this limit to exist, and we'll call this limit the derivative. And here's where our assumptions come in handy. The first one of them being that f of z satisfies the Cauchy-Riemann equations. Notice that if I just factor out a term of I from here, giving me an I term over here, and then I'll have a 1 by I term here, correct? Or I can just write that as negative I, but whatever. So in the denominator, we have 1 plus I times del y by del x, and we have this I times del y by del x as well. We want to get rid of this path-dependent term, meaning that we should have exactly the structure over here, right? This is exactly what we need. And how on earth are we going to convert this monstrosity into 1? Well, thankfully, again, we have the CR equations. In the denominator, we have the partials with respect to x. So let me just convert the partials with respect to y in the numerator into partials with respect to x using the CR equations. We know that partial u by partial y is in fact negative of partial v with respect to x, and we also know that partial v with respect to y is in fact partial u with respect to x. Okay, cool. That means in the denominator, what exactly do we have now? We have a 1 by I term, that is a negative I, times this partial u by partial y, so the two negatives cancel out quite nicely. We have partial v by partial x, plus partial u by partial x, which is exactly what we needed, because this is exactly what's in the denominator. So you have some wonderful cancellation here. You're left with 1 plus I times del y by del x, which cancels out perfectly with the with the numerator now. And all that's left here is just 1. So this implies that the limit L, which is in fact the limit as z approaches z naught, of f of z minus f of z naught divided by z minus z naught equals what exactly? This thing here, the only thing that's left. This is the limit as xy approaches x naught y naught of partial u by partial x plus I times partial v by partial x. And of course, we assumed the continuity of the first partials. So that means this thing here just evaluates out to the partial derivative of x of u with respect to x evaluated at x naught y naught, or just z naught, plus I times the partial derivative of b with respect to x at z naught. So the partial derivatives of the real and imaginary parts are defined on the set U. They're continuous on the set U. That means the left-hand side of this equation, that is the limit of the difference quotient, exists, and it's nice and continuous for any complex number z naught belonging to the set U. So yes, we have a derivative and the function f is analytic. Now that we're formally acquainted with analytic functions, let's take a look at a very important one. I'm talking about the function f of z defined as e to the z, the complex exponential, which can be expanded as e to the x times the cosine of y, plus I times e to the x times the sine of y. So if we label these functions as u and v, and first up, we want to differentiate with respect to x. So partial u by partial x is e to the x times the cosine of y, and partial v by partial x is e to the x times the sine of y. Now for the derivatives with respect to y, we have negative e to the x times the sine of y, and we have the partial derivative of v with respect to y being equal to e to the x times the cosine of y. So now that we have this array of data, we see that these two derivatives are equal, and if you add a negative sign, then these two derivatives are equal as well, and the CR equations are satisfied. Also, we see that all the partial derivatives are just products of exponential and trig functions. So yeah, they're nice and continuous, meaning that f of z is indeed analytic. So we can evaluate the derivative of the function f along any path we please. We'll choose the path along the real axis. So we can evaluate it as partial f by partial x. And this gives us this thing here, this column that is, excluding the negative signs in orange. So we have e to the x times cosine y plus I times the derivative of the imaginary part. So that is e to the x times the sine of y. Okay, great. And this is exactly what the complex exponential is. So the derivative of e to the z with respect to z is, as expected, the exponential function itself, which is pretty damn cool in a sense, or maybe it's just really obvious. I mean, we wanted an exponential function anyway. Yeah, exponentials were just defined to make calculus easier, I guess. Anyway, cool. So this is what we call an entire function. It's an entire function, meaning that it's analytic in the entire complex plane. So that means functions defined in terms of the exponential function, like the trigonometric functions or the hyperbolic functions, are entire functions too. And you can prove that the derivatives in the complex realm follow exactly the same pattern as the derivatives in the real realm. So we have these derivatives for sine and cosine, and of course you have corresponding derivatives for the other trigonometric and the hyperbolic trigonometric ratios as well. And that's not all for analytic functions. We're going to continue this in the next video as well. We're going to be looking at some important operators, some important notations as well, and hopefully we'll have enough time to study inverse mappings as well. Till then, I hope you enjoyed the video. I hope you learned something. Thank you. See you next time.